All right, so what we just proved in part B is sometimes called the Cauchy criterion. And the Cauchy criterion basically says that in the reals and the complex numbers, if you want to show that a sequence converges, it's enough to show that it's Cauchy. And so we're going to be using that in studying series of complex and real numbers, okay, because that's going to have some interesting applications. So here's a problem. It says, let a sub n be a sequence of non-negative real numbers such that the series converges. If you add all of them from n equals 1 to infinity, that's going to converge, meaning that this actually equals a real number. If z sub n is a complex sequence satisfying this inequality, meaning the modulus is always going to be bounded by this, show that the series of z sub n's converges. Okay, and so this is kind of a little interesting, I think intuitively, and this is of course not formal at all, but if we know that the modulus of Zn is less than or equal to a sub n, and I kind of think about taking the infinite sum of this and the infinite sum of this, and we know that this converges, we can almost kind of think of the convergence test, and then this would just converge as a result. Unfortunately, we can't do that because you can't apply the summation operator to both sides of an inequality if it's an infinite sum. Okay, that's just not something that you can do in general because there's all these questions about rearrangement and stuff. So instead, we're going to use the Cauchy criterion. So what we're going to do is this says first that a sub n converges. So let's just write out what that even means for a series to converge. Okay, so this is a little bit, hopefully, of review from Calc 2. But first thing that we're going to do is we're going to define the partial sums, right? So the partial sum Sn is going to be the sum of everything, and then we have to use maybe from k equals 1 all the way up to n of the a sub k's. Okay, and I defined it like that so that in order to show that, well, if we know that a sub n converges, this infinite series, that's going to imply that the sequence of partial sums also converges. And we know how to work with converging sequences, sorry. Converges. Okay, so what does the Cauchy criterion say about the sequence? Well, the Cauchy criterion would say something like, well, this happens if and only if, for every epsilon, my writing's not on par today, for every epsilon positive, there exists some sort of threshold in the natural numbers such that for any two natural numbers exceeding capital N, we have that an absolute value, the difference between Sn and Sm is less than epsilon. But we know that Sn and Sm are partial sums. Okay, so in other words, we have that this is equal to the sum from k equals 1 to n of the a sub k's minus the sum from k equals 1 to m of the a sub k's, and we know that that's less than epsilon. Okay, so let's roll with that for a little bit. Let's think about what that means. So we should probably kind of establish that in this case, maybe we'll just say like n is bigger than or equal to m in this case. I mean, one of them's got to be either bigger than or equal to or less than or equal to the other one. And so let's just assume it's like that. Okay, and so essentially what we have here is we have, a sub 1 plus a sub 2 plus yada, 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 all the way up to maybe a sub m plus a sub m plus 1 plus yada, yada, yada plus a sub n, right? That's this first term right here. And what we're doing is we're subtracting off every single term up to m. Okay, and so what we have here is this is going to be basically subtracting off, this term, all the way up to m. And so what's left over? Well, the thing that's left over is going to be everything from m plus 1 to n. So I'll say one more time, or the absolute value of the sum from k equals m plus 1 to n is less than epsilon. And the reason that's so nice is because this is a finite sum, and we can work with finite sums. Okay? Especially since, and I'm just going to work with this a little bit more, so this is going to imply what? Well, actually, let's just not do that. Okay, so that's what the Cauchy criterion would say about the difference between sums and sequences, and how all infinite sums are just sequences of partial sums. Okay, so that's pretty nice. Let's just go back up. Let's just scroll back up to what we're trying to show. So what we did is we essentially wrote what this means to converge using the Cauchy criterion. And now we're going to suppose that z sub n is a complex sequence satisfying this inequality. We're going to show as a result that this converges. And again, let's just use the Cauchy criterion. Okay, so what does the Cauchy criterion say? Well, we're going to take maybe some partial sums that we're going to define. We're going to show that z sub n minus z sub m is less than epsilon. Okay, so let's actually maybe start the proof now. We first should probably define some partial sums, and I don't really know what letter we should use here. Maybe, I don't know, B. So we'll say define, B sub n as the partial sums from k equals 1 to n of z sub k. Okay, and let epsilon be arbitrary. Okay, so we essentially want to show that, let's see, we want to show that there exists some sort of threshold. Well, what should that threshold be? Well, let's just look above, and we already kind of have that threshold here. All right, so let's just use that same threshold for the series of real numbers. Okay, so then we'll say for maybe n and m bigger than or equal to capital N, we have, and let's figure out what this is. So we have, well, b sub n minus b sub m, right? Because this is a sequence. This is a sequence. This is a sequence of complex terms, and we're going to show that it converges. Okay, so again, by kind of the same logic, we can show that this is equal to, using the same work as above. This is just equal to the sum from, k equals m plus 1 to n of the z sub k's. Okay, and now we have a finite sum, which means by the triangle inequality, and really, we haven't proved this. You can prove it very easily using induction. I technically didn't show that if I have like 3 terms or finitely many, this is less than or equal to the modulus of z1 and z2 and z3, You can show that for finitely many terms just with induction. So I can really just say that this is less than or equal to, and I can pull the sum out. Like that. But then wait a minute, we know something about the moduli. We know that the modulus of z sub k is always less than or equal to a sub k. And a sub k has to be non-negative, because if it were negative, then this wouldn't make sense because this is a positive number. Okay, so that's kind of why that was stated. Okay, so then we have that this is going to be less than or equal to the sum from k equals m plus 1 n of a sub k. And let's look above. That is exactly what we have right here. and that's less than epsilon, just by the definition of the series of real numbers converging. So we get basically for free, that this thing is less than epsilon. All right, so that's the proof.